A single star can unleash more energy than our sun will in its entire lifetime. We are embarking on a journey to witness the 25 most powerful explosions ever recorded in the vast theater of space. You will discover cosmic events so immense they outshine entire galaxies and forge the very elements that make life possible. What happens when a star gets too close to a monster black hole, and why do some stellar deaths remain a complete mystery to science? What do you believe is the most violent force at work in our universe today? Our journey begins not with a whimper, but with a cosmic blast so immense it redefines the very idea of power. We must start with the ultimate stellar detonation, a hypernova. Think of it as the universe's own Tsar Bomba, an event that makes a typical supernova look like a mere firecracker. This cataclysm is born from the death of a true stellar giant, a star so massive its core cannot endure its own weight. At the very end of its life, this colossal core collapses instantly. It does not explode outward, but rather implodes, falling inward at a staggering fraction of the speed of light. This sudden, violent collapse triggers a rebound effect of almost unimaginable force. A shockwave erupts from the star's heart, tearing the entire structure apart and unleashing more energy in a few seconds than our sun will produce over its entire 10 billion-year lifetime. The flash of light from a hypernova can, for a brief, brilliant moment, outshine the combined light of every star in its host galaxy. It is a true cosmic beacon, a final, defiant roar from a star that lived and died on an epic scale. What other celestial events could possibly compete with such raw, universe-shaking power? But that brilliant flash of light is only the beginning of the hypernova story. The true, lasting impact of this cosmic cataclysm unfolds in its violent aftermath. As the star's outer layers are blasted into space at nearly the speed of light, they form two incredibly focused jets. These jets erupting from the star's poles are the source of the most energetic form of light in the known universe, gamma rays. When one of these jets is pointed directly at Earth, we witness a long-duration gamma ray burst, a beacon of pure energy that can be seen clear across the cosmos. This is the hypernova's final, spectacular signature. But what is left behind after the fury subsides? The star's collapsed core faces one of two fates. It can be crushed into an object of infinite density, a newborn black hole, a gravitational pit so deep that not even light can escape, or under the right conditions it might become a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from every credit card on Earth from thousands of light years away. Yet this destructive power is also a creative one. The incredible heat and pressure inside the explosion forge elements far heavier than iron, like gold, platinum, and uranium. These newly forged atoms are then hurled into the void by the expanding shockwave, seeding ancient gas clouds with the raw materials for new stars, planets, and one day, even life itself. Every time you look at a piece of gold jewelry, you are looking at stardust forged in the heart of a cataclysm that outshone galaxies. So the next time you gaze at the night sky, remember that the quiet darkness is an illusion, a canvas for the very explosions that built our world. Far beyond the creative fury of a hypernova lies a flash of such impossible intensity it defies all earthly comparison. In 2004, a satellite's instrument screamed in overload, capturing a spike of energy from the darkest reaches of space. This was JRB 041219A, a gamma ray burst so phenomenally bright that for a handful of seconds, its light, which had been traveling for nearly 3 billion years, would have outshone the full moon in our own night sky. Imagine that for a moment, a single point of light from a source halfway across the observable universe, becoming brighter than the gentle, reflected glow we have known for all of human history. This was the death cry of a massive star, a hypernova event whose jet was aimed like a cosmic sniper rifle directly at our planet. The radiation that washed over our satellites was a final message from a star that died when Earth was home to only single-celled life. It carried the signature of raw creation, of atomic nuclei being forged in a stellar fire, and of a black hole being born in an instant of supreme violence. This event, catalogued now in astronomical records, stands as a permanent testament to the fact that the universe is not a quiet, static painting, but a dynamic and often violent arena. What other celestial bullets might even now be streaking toward us, carrying the light of ancient apocalypses? The sheer duration of that brilliant flash held the key to its violent origin. JRB 041219 did not vanish in a split second. Its gamma-ray signal persisted for hundreds of seconds, a clear fingerprint pointing to the collapse of a truly massive star. This was no merger of two dense stellar corpses. This was the core collapse of a stellar giant, a behemoth that had lived fast and died young in a cosmic blaze of glory. Its long, lingering scream of energy was the sound of a star's entire structure being unzipped from the inside out, yet the initial burst of gamma rays was only the opening chapter. As the expanding shockwave from the explosion plowed into the thin gas of interstellar space, it created a secondary glow that could be studied for weeks. This was the afterglow, a fading ember that allowed astronomers to decode the blast's deepest secrets. By training the world's most powerful telescopes on this faint, lingering light, they could dissect its spectrum, breaking it down like a cosmic rainbow to reveal its chemical composition. Each element leaves a unique barcode in the light, and the afterglow of JRB 041219 was a rich tapestry. It revealed the presence of iron and other heavy elements, the very atoms forged in the star's final moments and then blasted into the void by the explosion. This was the direct evidence of cosmic alchemy, the process that seeds the galaxy with the building blocks of worlds. The structure of the fading light also painted a picture of the explosion's geometry, confirming the existence of those narrow, ultra-powerful jets. Without the precious data from the afterglow, this cosmic catastrophe would have remained just a brilliant, mysterious flash. Instead, it became a detailed textbook on stellar death. What other secrets might be hidden in the faint, fading light of other cosmic cataclysms? While we study these distant flashes with satellites, humanity has witnessed cosmic explosions with the naked eye. In the spring of the year 1006, a new star blazed into existence in the southern sky. Chinese, Egyptian, Japanese, and European astronomers all recorded the same astonishing sight, a guest star that suddenly shone brighter than Venus. For weeks, this brilliant point of light was even visible during the day, casting faint shadows at night. Modern science has identified this event as supernova 1006, the brightest stellar explosion in all of recorded human history. It was the violent death of a white dwarf star, a stellar cinder that had greedily pulled material from a companion star until it reached a critical mass. This triggered a runaway thermonuclear explosion that utterly annihilated the star, a cosmic bomb of incalculable power. The light from that detonation traveled for over 7,000 years before finally reaching Earth, arriving as a silent, celestial flare that captivated cultures across the globe. They saw it as an omen, a portent, or a divine messenger. They had no way of knowing they were watching a star commit suicide, an event so powerful its faint, expanding remnant can still be detected today. That ghostly cloud of gas, still racing outward at millions of miles per hour, is the final, fading echo of a blast that once dominated the human sky. What must it have been like to look up and see the familiar heavens permanently and terrifyingly changed? The ghost of that ancient supernova still haunts the cosmos today. Known to astronomers as SN 1006, its remnant is a vast frayed tapestry of gas, still racing outward into space at thousands of kilometers every second. If you could see it with the naked eye, it would appear as a faint, wispy shell of light, a celestial bubble growing ever larger, but our eyes cannot perceive its true nature. To understand this cosmic aftermath, we must listen to it in X-rays and radio waves. Through these invisible eyes, the serene veil is torn away to reveal a scene of utter chaos. The remnant glows fiercely in X-rays, a testament to gas heated to millions of degrees by the original blast wave. This is not a gentle expansion, but a continued, violent shoving match as the shockwave plows into the cold, thin material of interstellar space. At the very heart of this maelstrom lies the cinder of the star that exploded, a rapidly spinning neutron star known as a pulsar. This city-sized object, denser than any material we can conceive, spins dozens of times every second, whipping its magnetic fields around to lash the surrounding nebula with intense radiation. It is the stellar corpse, the engine that continues to energize the expanding wreckage. The entire system is a cosmic crime scene, and the evidence left behind, The hot gas, the shock waves, the spinning pulsar allows us to reconstruct the precise moment of detonation that so captivated our ancestors 1,000 years ago. It is a direct link between a historical observation and a modern astrophysical reality. Just over 400 years ago, the sky produced another celestial omen for the world to ponder. In the autumn of 1604, a new star ignited in the constellation Ophiuchus, shining so brightly it rivaled Jupiter itself. This was Kepler's supernova, and its witness, the brilliant astronomer Johannes Kepler, did more than just stare in awe. He studied it meticulously, night after night, for over a year. His detailed records were a treasure trove of data, but they carried a weight far beyond simple observation. This new star was a direct challenge to the ancient, deeply held belief in a perfect and unchanging cosmos beyond the moon. According to the teachings of Aristotle, which had dominated Western thought for nearly 2,000 years, the heavens were immutable. The sudden, violent appearance of a new star shattered that dogma. It was undeniable proof that the realm of the stars was not a static backdrop, but a place of dynamic change and cataclysm. Kepler was living through a scientific revolution, and this supernova was a key piece of evidence, a cosmic bomb that helped blow apart an outdated view of the universe. What other long-held truths might be shattered by the next great flash in the dark? The legacy of Kepler's supernova is not confined to the history books. Modern astronomy has returned to the scene of that ancient explosion, and what it found reveals a far more complex and violent event than Kepler could have ever imagined. The remnant of SN 1604, a tangled, expanding cloud of gas and dust, glows fiercely in X-rays. This high-energy light tells a story of extreme conditions. It reveals the presence of vast amounts of iron and silicon, elements forged in the heart of the explosion and then blasted outward. But the specific mix of elements and the structure of the remnant point to a particular kind of stellar death. Kepler's supernova was a type Ia, the total thermonuclear detonation of a white dwarf star. This white dwarf likely had a companion star, slowly siphoning material from its neighbor until it reached a critical mass threshold. The resulting explosion was so perfectly calibrated by physics that its intrinsic brightness is nearly universal. This makes type Ia supernova standard candles, cosmic mileposts that astronomers use to measure vast distances across the universe. The light from Kepler's star, therefore, did more than just challenge ancient philosophy. It helped lay the groundwork for the tools we would later use to discover the accelerating expansion of the cosmos itself. One star's death became a fundamental ruler for measuring the universe. The heavens themselves seemed to rebel in 1572. That November, a new star, brighter than Venus, appeared in the constellation Cassiopeia. It was witnessed across Europe, but one man, the Danish nobleman Tycho Brahe, refused to accept the simple explanation. Armed with his own meticulously crafted instruments, he set out to measure the star's position night after night. His goal was simple yet revolutionary: to determine if this new star was a nearby atmospheric phenomenon or something immeasurably farther away. If it were close, its position should shift slightly against the backdrop of the fixed stars, an effect known as parallax. Night after night, his measurements revealed no such shift. The new star displayed no parallax whatsoever, proving it was not a flicker in Earth's atmosphere, but a genuine stellar event residing in the realm of the distant stars. This was a stunning, concrete blow to the ancient Aristotelian belief in an unchanging celestial sphere. The heavens were not perfect and immutable. They could change and they could explode. Tycho's supernova did more than just light up the sky. It lit the fuse for a scientific revolution, providing the first solid observational evidence that the cosmos was a dynamic and evolving place. His precise data would later prove invaluable to his assistant, Johannes Kepler, in formulating the laws of planetary motion. How many other cosmic truths were waiting, hidden in plain sight, for someone with the patience and precision to measure them? Centuries before Tycho Brahe trained his instruments on the sky, another star met its end in a display of even greater brilliance. In the summer of 1054, a new star erupted in the constellation of Taurus, shining with a light that rivaled the planet Venus. For 23 consecutive days, it was so intensely bright that it was clearly visible in broad daylight, a terrifying and awe-inspiring sight for cultures across the globe. Chinese court astronomers meticulously recorded this guest star, while observers in the Islamic world and likely Native Americans in the southwestern deserts also noted its sudden, silent appearance. Then after nearly 2 years of dominating the night, it faded from view, leaving behind a mystery that would linger for generations. What remained after that colossal flash of light was invisible to the human eye, a secret held by the darkness for almost 700 years. When powerful telescopes finally turned toward that patch of sky, they revealed not a void but a beautiful chaotic cloud of glowing gas. We call it the Crab Nebula, the expanding wreckage of that very supernova. This cosmic cloud is not a static painting. It is a living entity, still racing outward at over 1,000 kilometers every second. But what keeps this nebula shining so brightly, so many centuries after the initial explosion? The answer lies at its very heart. There, spinning 30 times every second, is the crushed core of the star that died, a pulsar. This city-sized neutron star acts as a relentless cosmic engine, its intense magnetic field and rapid spin accelerating particles to nearly the speed of light. The nebula glows because this pulsar is pouring energy into it, lighting up the expanding gases from within like a celestial lighthouse trapped inside its own fog. Every time we observe the Crab Nebula, we are witnessing the ongoing aftermath of a single titanic detonation, a stellar corpse continuing to power its own magnificent funeral shroud. Some stellar explosions do not destroy the star. In the 1840s, the southern sky witnessed a different kind of cataclysm. The hypergiant star Eta Carinae, a true stellar behemoth containing over 100 times the mass of our Sun, began to tear itself apart. It did not go supernova. Instead, it underwent a colossal stellar eruption, an event so violent it ejected at least 10 times the mass of our entire Sun into space. For over a decade, this titanic outburst made Eta Carinae the second brightest star in the entire night sky, a brilliant beacon of cosmic instability. It was as if the star developed a fever, swelling to an immense size and shedding its outer layers in a desperate, convulsive effort to survive. This was not a final death, but a near-death experience on a cosmic scale. The star survived, but it was forever scarred by its own fury. What remains today is one of the most beautiful and bizarre structures in the galaxy, the Homunculus Nebula. This hourglass-shaped cloud of gas and dust is not the remnant of an explosion that shattered the star, but rather the fossilized evidence of that great eruption. The nebula is made of the material the star violently coughed out over 150 years ago, a pair of vast lobes expanding outward, still illuminated by the furious light of the central star hiding within. This event forces us to ask a profound question: what could possibly cause a star to undergo such a violent, self-destructive fit without actually ending its life? The leading theory points to the star's incredible mass. The radiation pressure burning within its core was so immense that it began to overwhelm the force of gravity holding the star together. Eta Carinae became so luminous it was literally pushing its own outer layers away. This created a state of extreme instability, likely culminating in a massive outburst that ejected enough material to temporarily lower the internal pressure and allow the star to restabilize. It was a cosmic pressure valve being released with the force of a minor supernova. The Homunculus Nebula stands as a permanent monument to that release, a beautiful glowing tomb for the star that once was, built by the star that still remains. This was not a final death, but a dramatic, violent episode in the life of a true stellar monster. But that beautiful nebula is also a warning. Eta Carinae is a ticking time bomb, and its eventual death is predicted to be one of the most spectacular events our galaxy will ever witness. The reason for this lies in its staggering mass. Even after its great eruption, this stellar monster still holds the mass of at least 90 suns. It is teetering on the very edge of stability, burning through its nuclear fuel at a furious, unsustainable rate. When a star this massive finally runs out of fuel, its core will not just collapse, it will implode with a violence that could produce a hypernova, the very kind of event that powers long gamma-ray bursts. The question is not if Eta Carinae will explode, but when and with what consequences. Its relative proximity to Earth, at just 7,500 light-years away, makes this a deeply personal cosmic drama. A full-blown hypernova at that distance would be a celestial event unlike any in recorded history. For a few weeks it could shine as brightly as the full moon, visible even in broad daylight. The night would temporarily cease to exist, bathed in an eerie, constant silvery light from a single brilliant point in the sky, but that breathtaking light show could carry a hidden danger. If one of the hypernova's polar jets were to be pointed anywhere near our solar system, we would be bathed in a torrent of high-energy gamma radiation. While our atmosphere would shield us from the worst of it, such an event could still have significant effects, potentially damaging our protective ozone layer and altering the chemistry of our upper atmosphere. It would be a stark reminder that we live in a dynamic and sometimes hazardous universe. The Homunculus Nebula is not just a monument to a past eruption, it is the prelude to an even greater cataclysm, one that could write the next chapter in humanity's relationship with the stars. Long after the light of Eta Carinae's future explosion fades, the ghost of another stellar cataclysm continues to unfold in our own galactic neighborhood. Drifting through the southern constellation of Vela is the magnificent remnant of a supernova that detonated a mere 11,000 years ago. In cosmic terms, this was practically yesterday, a stellar death that occurred well after the last ice age ended and human civilizations began to form. If our ancestors had the means to record it, they would have seen a new star blazing in the sky for weeks on end. Today, we see the spectacular aftermath, a cloud of expanding wreckage so vast it spans over 100 light years from end to end. This is not a simple spherical bubble. Through the eyes of our most powerful telescopes, the Vela supernova remnant reveals itself as a tangled, intricate web of glowing filaments. Strands of gas heated to millions of degrees shine with a faint ethereal light and X-rays, while other cooler filaments glow in visible hues of pink and orange, a celestial tapestry woven from the death throes of a star. The entire structure looks less like an explosion and more like a cosmic brain, a luminous, chaotic network of stellar neurons firing in the void. What incredible forces could sculpt gas on such an immense scale into these delicate, thread-like forms? The answer lies in the violence of the original blast and the turbulent environment it exploded into. The initial shockwave, racing outward at thousands of kilometers per second, did not expand into a perfect vacuum. It encountered pockets of denser and thinner interstellar material. As the wave plowed through this uneven landscape, it created instabilities, causing the expanding gas to twist and fold back on itself, forming the delicate, rope-like structures we see today. It is a fossilized record of a complex interaction, a snapshot of a shockwave frozen in time, but the true heart of this cosmic cloud holds an even more fascinating secret. Deep within this luminous maze spins the Vela pulsar, the ultra-dense spinning corpse of the star that created this entire spectacle. This city-sized neutron star rotates an incredible 11 times every second, and with each rotation, it sweeps a beam of radiation across the cosmos like a frantic celestial lighthouse. The energy it pumps out continues to illuminate and energize the entire nebula, preventing the fading cloud from dissipating into the darkness. Every delicate filament, every glowing thread of gas is being constantly re-energized by the frantic spin of the dead star at its center. We are not just looking at an ancient explosion, we are witnessing an ongoing dynamic relationship between a stellar corpse and its magnificent funeral shroud. That frantic spin in Vela is a reminder that stellar corpses are the true engines of these cosmic clouds. But in the winter of 1987, astronomers witnessed a stellar death in real time, an event that would become the most studied supernova in history. On February 23rd, a brilliant new star ignited in the Large Magellanic Cloud, a small satellite galaxy orbiting our own. This was supernova 1987A, the first nearby supernova visible to the naked eye in over 3 centuries. For the global community of astronomers, it was a cosmic gift, a laboratory for stellar death unfolding right in our celestial backyard. The initial flash of light was just the beginning. Hours before that visible light reached Earth, underground detectors in Japan and the United States registered a fleeting, ghostly pulse. They had captured 24 neutrinos, subatomic particles so elusive they can pass through entire planets without a single interaction. This was the direct signal from the star's collapsing core, the first and only time we have ever observed the birth cries of a neutron star in real time. It was a stunning confirmation of long-held theory, proving that the core collapse of a massive star truly does produce an immense burst of these ghostly particles. The light told us a star had died, but the neutrinos told us exactly how it happened, a profound moment for all of science. What else could we learn by watching the aftermath of this cosmic crime scene unfold? The story of SN 1987 deepened with every passing year. The star that exploded was not a red supergiant, as most models predicted, but a blue supergiant. This single detail forced a major revision in our understanding of stellar evolution, proving that massive stars can take unexpected paths right up to their final moments. Then, as the initial flash faded, the real show began. The expanding shockwave from the explosion, traveling at tens of thousands of kilometers per second, began to slam into a ring of material the star had ejected 20,000 years earlier. This collision, predicted by theory, was spectacularly confirmed. The ring, previously dark and invisible, lit up like a string of cosmic pearls as the shockwave heated it to incredible temperatures. Over the following decades, the Hubble Space Telescope watched as this ring of fire grew brighter and more complex, a perfect demonstration of how a supernova's shockwave interacts with its pre-existing environment. More recently, new observations have revealed the presence of a dusty central source, likely the newborn neutron star itself, finally revealing itself after being hidden for years within the expanding debris. The continued observation of SN 1987 is like reading a detective novel, one chapter at a time, with each new technological advance allowing us to uncover another piece of the puzzle. It transformed a single brilliant flash into a decades-long lesson on the violent and beautiful end of stellar life. While we were watching the slow, beautiful evolution of SN 1987A, the universe delivered another gift, this time from our own cosmic backyard. In May of 2023, a star in the magnificent Pinwheel Galaxy, a mere 21 million light-years away, reached the end of its life. This was SN 2023X, the closest supernova of its kind in over a decade, and it exploded into view at a time when our observational power was greater than ever before. This was not a historical record from 1,000 years ago, nor a faint flicker from a distant galaxy. This was a stellar death captured in real time with an almost unprecedented level of detail from the very first moments of its violent birth. Amateur astronomers were the first to sound the alarm, spotting the new point of light in a familiar spiral arm. Within hours, the world's most powerful telescopes, from the Hubble Space Telescope to the giant Keck Observatory in Hawaii, swiveled to focus on this new cosmic beacon. They did not just see a star that had exploded, they saw the explosion itself unfolding before their electronic eyes. The data they collected was a treasure trove, a minute-by-minute account of a stellar catastrophe. The light from the supernova revealed the chemical composition of the material being blasted outward, allowing scientists to essentially perform an autopsy on the star to determine what kind of giant it had been in life. This immediate, intimate view gave astronomers a front-row seat to the complex physics of the shockwave as it broke through the star's surface and raced into space. What secrets could this nearby cataclysm reveal about the final, desperate hours of a star's existence? The answer was hidden in the light's very behavior during the first critical days. The early data held a stunning revelation. In the hours immediately following the explosion, the light from SN 2023X did not simply rise to a peak, it exhibited a strange, rapid brightening. This fleeting signature was the key to understanding the star's final moments. Astronomers interpreted this as the shockwave from the collapsing core slamming into a cocoon of dense material that had surrounded the star. Just before its death, the star had undergone a period of violent convulsions, shedding enormous amounts of its own outer atmosphere into space. This meant the star was not quiet and stable in its final years. It was actively tearing itself apart, casting off its own skin in a series of pre-explosion eruptions. The supernova's light curve became a direct recording of that shockwave, hitting this circumstellar material, a fossilized record of the star's death throes preserved in the pattern of its light. For the first time, we had a detailed timeline of not just the explosion, but the agonizing prelude to it. This single event is now forcing a rewrite of our models for how the most massive stars behave in their final years, suggesting their deaths are preceded by a period of intense, unstable activity. The legacy of this nearby explosion will echo for years in scientific papers, helping us to better predict when and how other stellar giants in our local universe will meet their spectacular ends. That intimate autopsy of a nearby supernova reveals a star's final, violent convulsions. But what if the star's death is not its own doing, but a murder by an invisible cosmic predator? Far from the chaotic freedom of stellar explosions, there exists a more gruesome and meticulously violent end for a star. This is the fate of any sun that wanders too close to a supermassive black hole, a gravitational titan lurking at the center of most galaxies. The star does not simply vanish into the darkness. Instead, it is subjected to an unimaginable force, a process known as a tidal disruption event. The key to this destruction lies in a simple principle: the force of gravity weakens with distance. As a star approaches the black hole, the side of the star facing the monster feels a vastly stronger gravitational pull than the side facing away. This difference in pull, the tidal force, stretches the star horizontally while simultaneously compressing it. The star is not just pulled, it is physically ripped apart, spaghettified into a long, thin stream of incandescent gas. The star's own gravity, which once held it together in a perfect sphere, is utterly overwhelmed by the black hole's immense tidal grip. In a matter of hours, a sun like our own can be shredded into a swirling, chaotic river of plasma. But the violence of the death is only the prelude to a brilliant, final display. What happens to all that stellar material once the star is torn to pieces? The stream of gas does not all fall directly into the black hole. Instead, it gets tangled by its own momentum, forming a vast, hot, and incredibly bright accretion disk that swirls around the event horizon like water circling a drain. As this material, the remains of the star, rubs together at tremendous speeds, it heats to millions of degrees, shining with an intense flare of light that can outshine the galaxy's core for months. This is the tidal disruption event signature, a beacon of catastrophic consumption. We are not seeing the black hole itself, but the last scream of the star it just destroyed, converted into pure radiation. Each of these events is a cosmic feeding frenzy, a temporary blaze that marks a single star's sacrifice to the silent, dark giant at the center of its galaxy. The shredded stellar material does not vanish silently into the abyss. In 2014, a robotic telescope network caught a brilliant flare from a galaxy nearly 300 million light-years away. This event, cataloged as Assassin 14 Lie, offered astronomers a front-row seat to a star's gruesome execution by a black hole weighing millions of solar masses. This was not a single quick flash, but a slow-motion cosmic explosion unfolding over many months. For the first time, scientists were able to track the entire process across the electromagnetic spectrum, from radio waves to X-rays. The initial ultraviolet and optical light came from the outer layers of the star being violently stretched and heated during the tidal disruption itself. But the real story was told in X-rays. As the stellar debris swirled into a vast hot accretion disk around the black hole, friction heated the gas to temperatures of millions of degrees, causing it to shine with an intense, high-energy glow. This X-ray signal became a direct probe of the material closest to the event horizon, the point of no return. Meanwhile, radio telescopes detected something equally fascinating: vast outflows of material being ejected from the system, likely pushed away by the intense radiation pressure from the glowing disk. We were not just seeing a star being eaten, we were witnessing the black hole's table manners, a messy feast where as much material was flung back into space as was spiraling inward. The multi-wavelength view of Assassin 14 Lie transformed a single flare of light into a detailed dissection of a cosmic murder, revealing the precise mechanics of how a black hole consumes a star and the spectacular, glowing aftermath it leaves behind. That mesostellar feast pales in comparison to a far more precise and consequential cosmic collision. Deep in the void, two stellar corpses, each more massive than our sun yet compressed into a city-sized sphere, begin a final, fatal dance. These are neutron stars, the dense remnants of ancient supernova, locked in a decaying orbit by the relentless pull of gravity. For millennia, they spiral closer, and in the last milliseconds before impact, they rip each other apart in an event of unimaginable violence known as a kilonova. This is not the death of a single star, but the cataclysmic merger of two. The collision unleashes a blinding flash of gamma rays, a short, sharp burst lasting less than 2 seconds, a stark contrast to the long, lingering screams from collapsing massive stars. But the true wonder of a kilonova is not in the initial flash, it is in the spectacular aftermath. The extreme conditions generated in that collision, temperatures and pressures far beyond anything in a supernova, become a cosmic forge for the universe's heaviest elements. Here in a crucible of pure energy, neutrons are slammed into atomic nuclei at an incredible rate, building elements like gold, platinum, and uranium in a process called rapid neutron capture. A single kilonova can forge hundreds of times the mass of our entire planet in pure gold and other precious elements, then blast this newly minted treasure outward in a rapidly expanding, intensely radioactive cloud. The light from this cloud glows with a distinct reddish hue for days, a celestial signature of these heavy elements cooling down. So when you hold a gold ring, you are not just holding stardust, you are likely holding the ashes of a cataclysm that began with two dead stars smashing together in a dark corner of the galaxy. How many such cosmic foundries have operated over the eons to seed the universe with the very materials that make our technology and our jewelry possible? That historic flash of light in August 2017 was only half the story. For the first time, we did not just see a cosmic cataclysm, we heard it. The event began not with a telescope, but with a subtle shiver in the fabric of space-time itself. The twin detectors of LIGO in the United States registered a faint, rapid chirp, a gravitational wave signal that lasted for about 100 seconds. This was the sound of two neutron stars, each a perfect sphere just 20 kilometers across, spiraling toward their doom. Their final orbits, a dizzying dance of immense gravity, rippled outward across the universe at the speed of light. The signal was named GW1-70817, but then just 1.7 seconds after that gravitational chirp ended, NASA's Fermi Gamma Ray Space Telescope detected a short, weak burst of gamma rays coming from the same patch of sky. This was the moment the universe truly opened up to us. The gravitational wave told us what happened, the collision of two ultra-dense objects. The gamma ray burst told us the violent result, a kilonova. And now, with a precise location from the combined data, every major telescope on Earth and in space swiveled to watch the aftermath. This was the dawn of multi-messenger astronomy, the ability to observe a single cosmic event through both its ripples in space-time and its light across every wavelength. What would this new multi-sensory view reveal about the secrets of a kilonova? The answer unfolded over the following days and weeks. Optical telescopes were the first to spot it, a new faint point of light in the galaxy NGC 4993, 130 million light-years away. This was not a brilliant supernova, but something new, a glow that rapidly changed color from blue to deep red. This was the kilonova's signature, the radioactive glow of heavy elements being forged in the expanding cloud of debris. As astronomers analyzed its spectrum, they found the unmistakable fingerprints of cosmic alchemy, the telltale signs of elements like cesium, tellurium, and gold being created in real time. The data confirmed a profound truth, that the majority of the universe's gold, platinum, and other heavy elements are not made in the hearts of supernova, but in the violent mergers of neutron stars. Every precious metal on Earth was likely born in a cataclysm just like the one we were witnessing. The collision of GW1-70817 was not just an explosion, it was a cosmic foundry, proving that we are all, in the most literal sense, made from the ashes of dead stars. Even stellar death can sometimes be reversed. In the mid-1990s, a star in the constellation of Sagittarius did something astronomers thought was impossible. It came back to life. This was Saccharie's object, a white dwarf star that had already finished its life, having shed its outer layers to become a fading, Earth-sized ember. It should have spent eternity slowly cooling into a black cinder. Instead, it suddenly reignited. The white dwarf, in a final, desperate act of cosmic defiance, began fusing helium in its shell once again. This was not a supernova, but a slow-motion thermal pulse, a violent outburst that caused the star to swell back up to a red giant size over just a few years. It was a born-again star, replaying its final evolutionary stages at an astonishingly accelerated pace. For a brief, brilliant period, it became thousands of times brighter, a ghost star resurrected from its own ashes. This rare event challenged everything we thought we knew about the finality of stellar death, proving that some stars get a second act, a final dramatic encore before the curtain closes for good. What incredible forces could possibly restoke the fires of a star that had already burned out? The answer lies in a delicate and fleeting balance of physics. Just when the white dwarf seemed stable, a last reservoir of helium surrounding its core reached the critical temperature and pressure for fusion to begin anew. This fresh burst of energy did not explode the star, but instead caused it to expand violently, effectively reversing its own aging process in a cosmic time lapse. The star began ejecting massive amounts of its own mass, shrouding itself in a thick, carbon-rich cloud of dust. This created a living laboratory for astronomers to watch the late stages of stellar evolution unfold in real time, a process that normally takes thousands of years compressed into a single human decade. The violent rebirth of Sakurai's object shows us that the death of a star is not always a single definitive moment, but can be a complex series of fits and starts, a final sputtering candle flame that flares with unexpected brilliance before the true and permanent dark. That born-again star is a rare exception, a final flicker in a cosmos that usually extinguishes its lights for good. Far more often, a star's death is a definitive and brilliant punctuation mark in the dark. In the late summer of 1885, an astronomer named Ernst Hartwig was observing the great Andromeda galaxy through the telescope at the Dorpat Observatory in Estonia. He was studying that familiar spiral smear of light, our closest major galactic neighbor, when he saw something that should not have been there. Nestled right next to the galaxy's brilliant core was a new star-like point of light. This was S Andromedae, a supernova exploding inside another galaxy. Think about the sheer scale of that for a moment. Andromeda is so distant that its light takes 2.5 million years to reach us. Every other star you can see with your naked eye is a member of our own Milky Way, yet this one stellar detonation, occurring in a completely different island universe, was so phenomenally powerful that it pierced that unimaginable gulf of space. It briefly shone at a magnitude just visible in small telescopes, a cosmic shout heard across the intergalactic void. This was the first supernova ever recorded in another galaxy, and it delivered a profound message. The universe was not just a collection of static, unchanging nebulae. It was alive with violent change, with stars being born and dying in galaxies far beyond our own. It proved that the cataclysms we witnessed in our Milky Way were not local oddities, but universal constants, a fundamental part of the cosmic cycle playing out in every corner of the observable universe. Every pinprick of light in a deep-field telescope image represents a galaxy, and within each one, stellar life cycles of creation and destruction are continuously unfolding, mostly unseen, but occasionally announcing themselves with a flash that can cross millions of light years. Sometimes a star's corpse is given a violent kick at birth. After the core of a massive star collapses into a neutron star, the resulting supernova explosion is not always perfectly symmetrical. In a cosmic stroke of immense imbalance, just a fraction more matter and energy might be ejected in one direction than in another. According to the simple, unyielding law of action and reaction, this lopsided detonation can launch the newborn pulsar itself away from the blast site at an incredible speed. This is precisely what happened to the pulsar known as IGRJ 11,014-6103. It is a celestial cannonball, a city-sized object of unimaginable density, racing through the void at over 4 million miles per hour. At that staggering velocity, a journey from Earth to the Moon would take less than 5 minutes, but its speed alone is not its most spectacular feature. As this runaway pulsar plows through the thin gas of interstellar space, it is behaving like a cosmic speedboat on a lake. Its powerful magnetic field, trillions of times stronger than Earth's, acts as a prow, carving a bowshock through the surrounding material and accelerating particles to near light speed. This process creates a brilliant, comet-like tail that stretches for light years behind it, glowing fiercely in the high-energy light of X-rays. This luminous wake, observed by space telescopes, is a direct and visible record of its frantic escape, a scar etched across the cosmos. The pulsar itself is a cosmic orphan, having fled the scene of its own violent birth in the supernova remnant, known as the Carina Nebula. It has long since left the expanding cloud of debris from the explosion that created it, a solitary fugitive on an endless journey through the galactic dark. What does this tell us about the chaotic nature of stellar death? The pulsar's trajectory is a permanent arrow pointing back to its origin, proving that the final moments of a supernova are not a clean, spherical burst, but a messy, unpredictable, and staggeringly powerful event that can literally hurl its own core into the abyss. Sometimes the most spectacular explosions are not deaths but cosmic collisions. In the constellation Scorpius, a seemingly ordinary star named V1309 Scorpii began behaving strangely. For years it was a flickering variable star, but then its pulses grew more rapid and intense, its light curve coiling tighter and tighter like a spring being compressed. Astronomers were watching a binary system, two stars that had been orbiting each other for millions of years, finally losing their orbital energy. They were spiraling inward, locked in a final, intimate dance. In 2008, their dance reached its climax. The two stars did not just collide, they merged, their outer atmospheres violently churning together. This titanic embrace triggered a massive outburst, a luminous red nova. The system's brightness increased by a factor of 10,000 in just over a week, blazing with a distinct, deep red hue before slowly fading away. This was not a supernova which destroys a star, nor a kilonova which smashes dead stellar cores. This was the explosive creation of a single, new star from two that came too close. The red color itself is a clue, coming from the vast cloud of dust and gas ejected during the merger, a cosmic smoke signal for this violent act of stellar unification. V1309 Scorpii was a happy accident, a new class of explosion discovered because we were looking at the right place at the right time. It revealed a previously hidden pathway for stellar evolution, proving that stars can meet a spectacular end not by collapsing or being eaten, but by merging into something new. How many other quiet stars in our galaxy are actually binary partners inching toward their own explosive reunion? The violence of stellar collisions and stellar rebirths are but sparks compared to the enduring fury of a true cosmic engine. Far beyond any single star's death, at the very heart of ancient galaxies, a different kind of explosion rages for millions of years. This is the quasar outburst, a continuous detonation powered by a supermassive black hole with an appetite of cosmic proportions. Imagine a gravitational pit so vast it could swallow our solar system whole, and then surround it with a whirlpool of gas and dust the size of billions of suns. As this immense disk of matter spirals inward, rubbing against itself at nearly the speed of light, it heats to temperatures of millions of degrees. The friction is so titanic that it converts matter into pure energy with an efficiency far beyond any nuclear reaction, shining with the light of a trillion stars. A single quasar can outshine its entire host galaxy, its brilliance visible clear across the observable universe. This is not a momentary flash, but a sustained galactic-scale explosion that can last for epochs. What could possibly fuel such an unthinkable beacon? The energy comes from the gravitational death spiral of matter itself, a continuous sacrifice to the black hole that converts infalling gas into the most luminous and persistent fire in the cosmos. But the light from the accretion disk is only part of the story. The true explosive power of a quasar often channels itself into two colossal jets. These are not gentle streams of light, but tightly focused beams of radiation and particles, blasted outward from the black hole's poles at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, far beyond the confines of their home galaxy, punching into the empty space between galaxies. Where these relativistic jets slam into the tenuous gas of intergalactic space, they carve out vast, glowing cavities and trigger secondary explosions that ripple across cosmic volumes. This is a force that does not just shine, it actively reshapes its entire environment, heating galactic gas pools to prevent new stars from forming and effectively putting a cap on the growth of the galaxy itself. The quasar is both creator and destroyer, a central engine whose outbursts dictate the life and death of stars on a galactic scale. Every time we point our telescopes at a distant quasar, we are witnessing the master switch of a galaxy, a control mechanism of almost godlike power burning in the void. The confirmation of a kilonova in 2017 was a scientific triumph, but the real work was only just beginning. The hunt was on for more of these cosmic gold factories, and in 2019, a new candidate emerged from the shadows. Designated as SS-17A, this event presented a fresh puzzle for astronomers. It began with a short gamma-ray burst, a telltale signature of a neutron star merger, but the subsequent glow was strangely faint and evolved far more rapidly than the model predicted. This was not a clean textbook case, it was a messy, complex reality. The faintness suggested that the viewing angle might have been off-axis, meaning we were not looking directly down the barrel of the jet, but seeing the explosion from a more oblique perspective. The rapid evolution of its light hinted at a different mix of elements being forged, or perhaps a lower mass of ejected material. Each piece of data from SS-17 was a clue, forcing scientists to refine their models and consider new possibilities for how these violent mergers can unfold. The challenge lies in the sheer distance and brevity of these events, making every new detection a precious and fleeting opportunity to test our understanding of the universe's most extreme physics. The excitement is not in finding a perfect match, but in uncovering the anomalies that push the boundaries of our knowledge. What other strange and wonderful variations of stellar death are still waiting to be cataloged in the dark? Just when we thought we had stellar death neatly categorized, the cosmos delivered a true enigma. In June of 2018, a robotic telescope scanning the heavens caught a flash in a galaxy 200 million light-years away. It was designated at 2018 Cow, but astronomers quickly gave it a simpler name, the Cow. This was no ordinary supernova. It exploded into brilliance far faster than any known stellar cataclysm, reaching peak brightness in just a handful of days. Its light was intensely blue, a sign of material heated to extraordinarily high temperatures, and it faded away with a speed that left scientists utterly baffled. This was the birth of a new class of cosmic mystery, the fast blue optical transient, or FBOT. These events are the cosmic equivalent of a flash in the pan, but on an unimaginable scale, shining with the power of a supernova, yet evolving at a pace that defies all conventional models. What kind of explosion could possibly be this bright, this blue, and this brief? The initial theories were as wild as the event itself. Was it a star being shredded by an intermediate mass black hole? Or perhaps a peculiar type of supernova where the shockwave breaks through a dense shell of material the star ejected just before its death? The intense blue color and rapid fades suggested the presence of a central engine, something continuously pumping energy into the expanding debris to keep it so hot and luminous for those critical few days. This pointed toward a newborn, highly active object at the heart of the explosion, like a rapidly spinning neutron star or even a newly formed black hole greedily accreting material from its surroundings. The Cow was not a clean, simple detonation. It was a messy, complex birth, a cosmic firestorm whose true nature remains one of the most compelling puzzles in modern astrophysics. How many other strange, fleeting flashes have we missed because they vanished before we even knew to look for them? From the quiet death of a white dwarf to the universe-shaking fury of a hypernova, these cosmic explosions represent the full spectrum of raw power in our universe. There are the engines of change, the ultimate recyclers, and the silent architects of everything we know. Each cataclysm, whether it forges gold in the collision of dead stars or seeds galaxies with the elements for future planets, is a fundamental part of the cosmic cycle. Black holes shred suns to power brilliant flares, while mysterious fast blue transients defy all our models, reminding us that for every question we answer, a dozen more ignite in the dark. This relentless violence is not meaningless chaos. It is the very process that built our world and made our lives possible. Every atom in our bodies was once hurled across space by such an explosion, a legacy of ancient starlight written into our very being. So the next time you find yourself beneath a clear, dark sky, look up, see beyond the tranquil points of light to the hidden dynamism, the brilliant births and violent ends playing out in the silence. Remember that you are living in the aftermath of cosmic detonations, on a planet built from stardust, in a universe that is forever exploding, evolving, and revealing its secrets to those who dare to watch.